That's another Dibs Physics video.
What's up, physics nerds? Mr. DeBello here, coming at you with yet another video. Be sure to like, favorite, comment, and subscribe if you like the content. I'm just joking. But what we're going to do is get into a new topic of freely falling objects today. You guys watched a bunch of videos, and we're just going to clarify a few of the things that you saw in the video and make sure that we're all on the same page. Speaking of being on the same page, you can follow along in your notes right now because we're going to the notes to take a few notes. So if you want to open up your notes to page 22, that's where we're going to be starting. So let's jump into this here. And go to page 22 where we talk about free fall. I make a bad John Mayer joke because he plays the song Free Fall. Anyways, moving on. Let's look at a few examples, and you should be able to answer these based on the videos that you watched yesterday. Hopefully you picked up on some of the main ideas watching those videos. I know I didn't give you guys any accompanying stuff because I wanted you guys really to think about just kind of the video in general. So what do you think is going to hit the ground first? A physics textbook or a piece of paper when they're held next to each other and dropped? So I don't know if whoever's teaching right now, if you want to take a textbook and this is throwing off the thing. So take a textbook and a piece of paper, hold them up next to each other and drop them. Which is going to hit the ground first? You guys should be able to predict that. Okay? So when you do this, you're going to predict that I would hope the book is going to hit the ground first, right? And you'd be right. That book hits the ground first. It's falling faster than the piece of paper, right? That's kind of the language we would use. So what if we put the piece of paper under the book? So here's the textbook, and we put that piece of paper under the book, and we drop them. Well, what's going to hit the ground first? Well, the paper is going to hit the ground first, right? That paper is going to hit the ground first, but the book is going to be right behind it. And what's the reasoning for that? Why do you think that is? Why does now the paper fall faster when the book is on top of it? You could have a little class discussion if you want. You could pause the video even. You guys really want to take it to the next level. Pause the video, talk about it. All right, so you paused the video and talked about it? Great. I'm going to assume maybe some of you said something along the lines of the book is heavier, so it's pushing down on the paper. And that would be sort of right. Sort of. But what if we put the piece of paper on top of the book? So here's the book, and we put the sheet of paper right on top of the book. And we drop them at the same time. I think the prediction a lot of you would make is that the book's going to fall faster and that paper is going to float down. Do it in class. See what happens. So now that you've done this, what you've noticed is that piece of paper stays stuck to the top of the book. Why in the world is this? So what happens here is, the paper and book hit the ground at the same time. And I think this is a really kind of unique thing that comes up. The paper and the book are going to fall at the same rate. But is the book pushing the paper down anymore? No. Right? So something fishy is going on here. What would happen if we dropped a hammer and feather? Right? On Earth. If we dropped a hammer and feather on Earth, the hammer hits the ground before the feather, just like the book and the paper. But if we drop them from the same height on the moon, they hit the ground at the same time. And you guys watch the video of that. You watch an actual video of people actually on the moon and this actually happening. And hopefully you watched some more of the videos and you learned that all objects, regardless of their mass, are going to fall at the same rate on Earth, on the moon, or on any planet. Everything falls at the same rate. This difference that we notice between a piece of paper and a book or a hammer and a feather is due entirely to air resistance. So let's ignore air resistance for a second. If we do that, we actually have a new constant value, and we call it little g. So little g is a specific acceleration. We could write instead we could write, A equals 9.81 meters per second squared as well. But we write it as G because this G is specifically gravity. You get what I'm putting down? All right. So this number is going to come up a lot as we proceed through. This is a constant value on Earth. All objects accelerate at this rate. One thing we are going to do is write G is pretty much equal to, a little squiggly equal sign, 10 meters per second squared. When we're doing problems, we don't need the precision of 9.81 meters per second squared a lot of the time, and simply rounding it to 10 will make the numbers work out a little easier and still give us an answer that's pretty close to real life. So we'll use 10 meters per second squared as our acceleration due to gravity on Earth if we neglect air resistance. Now, let's talk a little bit about air resistance. We are going to neglect air resistance in almost every case. We will do no calculations with air resistance this year. And that might seem like, we're not really talking about real life here. But there's a reason why we have to neglect it at the high school level. Let's talk about the two things that affect air resistance. Okay. The first thing is velocity. The faster you go, the more air resistance you experience. So a great way to think about this is putting your hand out the window of a car. If you've ever done that, put your hand out the window of a car. Sorry, it's my ice maker going off right now. I don't know if you guys heard that. Anyways, so if you put your hand out the window of a car going 10 miles an hour, you're barely going to feel a little breeze on your hand. But if you put it out on the highway going 60 miles an hour, you're going to feel it really pushing your hand. So the force of air resistance depends on velocity. So let's get the bigger eraser. That was annoying. There we go. Greater speed equals a greater air resistance. And the next thing that air resistance depends on is the area of the object perpendicular to the direction of motion. So let's come back to our car example. If you put your hand out the window like this, right, you're not going to experience much air resistance as the air comes in and hits your hand. But if you put your hand like this, you are going to experience more air resistance. And that is because the area of this surface is a lot smaller than the area of this surface. So it's that area perpendicular to the direction of motion. And the greater that area, the greater the air resistance. So kind of an example of this is, somebody on a parachute, right? So if we have somebody on a parachute, right, like here they are. So draw a very bad picture. Here's our parachute. So a parachute is kind of like this, right, for this person. And as they're falling, they are falling downwards, right? So that means the air is going upwards towards this parachute. So the area of this parachute perpendicular to the direction of the motion of the air, right, is going to slow this down and increase the air resistance. So a parachute increases that air resistance by increasing the surface area perpendicular to the direction of motion. Okay? So what I want to do is look at this lovely little problem here. So which encounters a greater force of air resistance, a falling elephant or a falling feather? And I want you to really think about this one, because I got this out of a kid's book. And what do you think the kid's book said the answer was? Well, the kid's book said that the answer was the feather. I don't know why it did that. That's weird. All right, anyways, here we go. It said the answer was the feather. The feather experiences a greater force of air resistance because it is falling, right, slower than the elephant would. But that's simply not true. The elephant is going to be falling faster, and we know a faster speed means more air resistance, and the elephant is going to have a greater surface area perpendicular to the direction of motion, so the elephant's going to have a way bigger force of air resistance. Air resistance can be confusing. So we're not going to spend any time calculating it this year. The big reason for that is because since air resistance depends on velocity, and as you fall, your velocity increases as you fall, you accelerate downwards. That means that we would need calculus to be able to talk about how one thing changes while another thing is changing at the same time. So since we don't know any calculus yet, we're not going to be able to look into air resistance. I would be a real jerk if I made you guys do that. That's a joke. It's funny because jerk is a change in acceleration over time, which is exactly what would happen if we took into account air resistance. It would be a jerk situation, literally. So anyways, bad physics jokes aside, they really don't hit the same when you're recording a video. It's really not the same. We are going to bring in two new equations. And I'm not going to spend time deriving them with you guys. But what I'll do is, why don't we actually just go to a new page somewhere in your notes and talk about all the equations that we have. You also will have these in your reference table. So in your reference table, one of the ones you have is this one, which you should be very familiar with at this time. This equation is only good, okay, at a constant speed. So if you're asked to find the distance something travels, it only works at a constant speed because this is an average velocity. So for an object that's freely falling, as you guys saw in all the videos, things that fall speed up as they fall. Things that fall speed up as they fall. So we need a new set of equations. We need to talk about acceleration. So we have this equation, a equals delta v over t. And this equation can be rewritten as a equals delta v, which is going to be final velocity minus initial velocity over t. This is probably the better way to write it out. Okay. Then we also now have a new equation, which is going to bring in displacement. Delta x equals vi times t plus 1/2 at squared. This is a ridiculously long equation, so I've named it El Grande. And then we're going to bring in another equation. This is vf squared equals vi squared plus 2a delta x. And this one is called the Boston equation. We'll talk about why in a second. So we've got the Boston equation, we've got El Grande, and we also have this one, which doesn't really have a name yet. We just often call it the acceleration equation, which I kind of like because it rhymes. The acceleration equation. Sounds good. So these three equations are going to help us solve really any of the problems that we need. Now, the reason we have these three is very, very important. Each of these equations is missing something. So let's look at all of the different variables that we have in these three equations. We have acceleration. We have time, we've got delta x, we've got vi, we've got vf, right? So we've got 5 different things that we could be solving for in any one of these problems or any kinematics problem. Each of these equations is missing something. So the acceleration equation has no delta x in it. So if we have a problem that doesn't have a distance given or isn't asking us about distance, we can use the acceleration equation to solve. El Grande has no final velocity in it. So this one doesn't have a final velocity in it, so we can use that in situations where we don't have a final velocity or aren't looking for it. And then finally, the Boston equation has no t, and maybe you'll understand why we call it the Boston equation now, because they have no t because they threw it all in the harbor. Okay, so what I would do if I were you guys is you have these equations on your reference table, but this is what I would throw on your reference table next to those equations so you know what thing you don't have in that equation. That's going to help us solve some problems. So let's kind of get into some problem solving stuff and talk about our process for solving these. So I'm going to jump in here to these problems. These are nowhere in your notes, so just follow along kind of with the video. And I'm going to go through some steps of problem solving. So let's start with step 1 of doing these problems is to make a chart. So the first thing we want to do when solving any one of these problems is make a chart. So I start by doing delta x, vi, vf, a, and t. And then I draw a line, and then what I do is I fill in on this chart what I know. So let's take a look at the problem and talk about what we know. A car is traveling at 20 meters per second to the north. Okay. Awesome. So we're given some numbers here, 20 meters per second. That is the initial velocity of this car. So I'll throw that in as the initial velocity. It accelerates at a rate of 2 meters per second squared. So I'm going to put that in as acceleration, right? What is the magnitude of its velocity after 8 seconds? So the time is going to be 8 seconds, and they want to know my velocity after 8 seconds. So I'm going to put a question mark for my final velocity. So now that we've made a chart, we've got to pick an equation to use. So what we do in step 2 is pick our equation. And we pick it based on what we don't have. And this is kind of weird. If you look at our chart, we have 3 of 5 things, and we're looking for 1 of those 5 things. But there's one thing that we don't have, and we don't care about it. We don't want to find it, and we don't have it. So that thing helps us choose our equation. So now, if I look back at our list of equations, what thing has no delta x in it? Our acceleration equation has no delta x. So I'm going to choose my acceleration equation. So I'm going to choose a equals vf minus vi over t. Okay, so I'm going to choose that equation. Now, let's go to step 3, algebra. Don't be a numbers girl. We do our algebra first. So I'm going to start with the equation. And what I'm going to do is I'm going to solve for the thing that I'm looking for. I'm looking for VF. So I want an equation that is VF equals blah, blah, blah. So let's get there. First, undo my fraction. So I'm going to multiply by t on both sides of the equation. So now I have a times t equals VF minus VI. So the t's cancel there. Beautiful. Ladies and gentlemen, that's where it's at. Okay, now I want to get VF by itself, so I'm going to move VI to the other side by adding it. Okay, so I do that, and now I'm left with my final equation of VF equals VI plus AT. So now, once I've done that, now it's time for step 4, solve. So in step 4, we plug in our numbers and we solve. So we start with our equation that we've rearranged, VI plus AT, and now all we've got to do is substitute in the value. So VF equals VI. Let's get VI. VI was 20 meters per second. So I'm getting this from the chart, plus my acceleration, which was 2 meters per second squared, times my time, which was 8 seconds. So now what we've got to do is get our calculator out. Let me just get my calculator real quick. Okay, there we go. And let's do 20 plus 2 times 8. So the beauty of doing our algebra first is we'll only need to go to our calculator one time to get our answer. So we end up with 36 meters per second. Now let's take a look at our units here and what's actually happening. So how did I know the units of this answer were meters per second? Well, I look at it and go, okay, seconds cancels with one of the seconds in the denominator, and then I have meters per second plus meters per second, which makes sense. Cool, we've got meters per second. However, we have an understanding here that if we use our standard units in these equations, we will get the standard units out of these equations. Since we solved for a velocity, our standard unit of velocity is meters per second, so we're ready to just write meters per second in for our final velocity. Okay? Now, one thing that I want to notice is we did not talk about directions here at all. We probably should have. Let's say, before we do this, north is positive and south is negative. If we do that, right, then when we make our chart, we got to be very specific about our positives and negative. Okay, we said 20 meters per second, that's to the north, we called it positive, great. Our acceleration is also to the north, so that's also positive, great. So did it change our answer at all? No. But what if we do the same problem, but with directions being a little different? So let's do the same problem here. We've got north being positive and south being negative. When we make our chart, I'm always going to make my chart in the same order. Delta X, VI, VF, A, and T. You don't need to make it in the same order. You can do it whatever order you want, but I always kind of like this order. VI here, we have a positive 20 meters per second because we're initially traveling to the north. However, our acceleration this time is to the south. So our acceleration is going to be negative 2 meters per second squared. So that negative sign is going to change how we do this problem. We still have the same 8 seconds, that's not affected by direction, and we're still looking for our final velocity. Delta X is the thing we don't have and don't care about, so that helps us choose our equation. And I'm just going to write VF equals VI plus A times T, right? The algebra has already been done. We already did it in the previous problem, so I'm not going to go through it again. But we've got 20 meters per second here, plus negative 2 meters per second squared times 8 seconds. So if I was to go to my calculator on this one, right, I'm going to be typing in mostly the same thing, but the calculator is going to take care of all of it for us, right? I'm going to do a negative sign, right? Negative 2 times 8. Bada boom. there we go, and we get an answer of now 4. So we get a very different answer here. Now, this final velocity is still going to be to the north. We got a positive answer, so that means we're still traveling north. But what happened to our velocity? Well, we were slowing down, right? So if you recall from some of the stuff we did last week, right, when acceleration is opposite the direction of motion, an object is going to slow down, right? So there we go. We've got 4 meters per second to the north. Now, did I need to write the north to get this correct? The answer is no, I did not. I did not need to write this to get this correct, and that's because of this word in the problem. What is the magnitude of its velocity? Just the amount, not the direction. Now, did we still have to take into account direction when we did the problem? Yes. So if you see the word magnitude, it doesn't mean ignore direction. It means you don't need to include it on your final answer, because we did need to take into account direction when we did the problem. We needed to make sure that this acceleration was a negative 2 meters per second squared. So hopefully that helped. Let's do a couple more examples, and then I'm going to break you guys loose and give you a whole bunch of assignments and a whole bunch of problems to solve. And hopefully this process helps. And you guys have hopefully gotten kind of comfortable with, in this class, working with a specific process. Okay, so this next problem. A car starts from rest and accelerates north at a rate of 4 meters per second squared for 10 seconds. What is the magnitude of the car's displacement? So we make our chart, delta x, vi, vf, a, and t. Now, we've got to think about direction. Should we have a positive direction in place? Yeah, anytime a problem specifies a direction, you see north, forward, backwards, to the right, to the left. Anytime you see that, that's a big warning sign that we should think about this. Let's make north positive, right? That's pretty standard. And south negative. You can never choose the wrong thing to be positive or negative. As long as you're consistent throughout the problem, you'll be good. So just make a decision. So a car starts from rest and accelerates north at a rate of 4 meters per second squared. All right, so that's an acceleration. Anytime you see that unit meters per second squared, that's an acceleration. So let's come down here for our acceleration, and let's put a positive 4 meters per second squared. Okay, awesome. And the car starts from rest. That's giving us some info. That's telling us our initial velocity is 0 meters per second. 10 seconds is the time that it's going to accelerate for. Boom, 10 seconds. What is the magnitude of the car's displacement? Ooh, so they want us to find delta x. So we fill out our chart with the things we have and the thing we're looking to find. And as you'll always notice, there's one thing that's left out. And from that, we'll choose our equation. So if we go back to our equation, the equation that has no VF is El Grande. Okay, so let's use El Grande as our equation. So delta x equals, I don't like this pen. I like the color though. I'm just gonna make it thinner. There we go. So delta x equals VIT plus 1/2 AT squared. Now there's something kind of nice about this equation this time. Our initial velocity is 0 meters per second. So when I go to plug in 0 for initial velocity, what's going to happen? What's 0 times 10 seconds? 0, right? So one of the things we can do is look at this and cross out this VIT and do a little arrow pointing towards a 0. When we do that, what we're doing is saying this whole term here, there's a 0 in there, and the whole thing is going to equal 0. So we can do that and then rewrite our equation without that term. So it simplifies El Grande now to El Not So Grande, a more manageable equation. So let's go and plug these in. We'll put our acceleration in as 4 meters per second squared, and our time as 10 seconds squared. So once we substitute into this equation, right, we didn't need to do any algebra this time. How cool was that, right? Delta x was already by itself, which is what we were looking for. So now all I've got to do is go, okay, 0.5 times 4 times 10 squared. So I plug that whole thing into my calculator. This is going to be something that plagues a lot of you. You're going to forget that squared. In this equation, it is t squared. And for whatever reason, you guys aren't really diligent when you're going through the problem-solving process, and you forget that squared. But let's hit enter on our calculator, get our number, and we've got 200 as our final answer. So delta x is equal to 200 meters. So there we go. There's our final answer. It said what is the magnitude of the car's displacement, so we don't need to give a direction, even though we know that that's 200 meters to the north because we were accelerating to the north. All right, guys, beautiful. Love it. We're crushing this right now. So let's keep it going. Let's do one more problem here. Okay, a car accelerates at a rate of 6 meters per second squared forward. Oh, so we got forward and backwards going here. Okay, let me get rid of the calculator so we can read this. If the car starts with an initial forward velocity of 8 meters per second, what will be the car's velocity after 10 seconds? Ooh. This one's kind of interesting, right? So let's go in and set up our chart. So we've got, delta x, vi, vf, a, and t. And we'll say forward is positive, backwards is negative. So when we go and put these things in, we'll be very specific. So a car accelerates at a rate of 6 meters per second squared forward. So forward's positive, so I'll just leave that as positive 6 meters per second squared. The car starts with an initial forward velocity of 8 meters per second. So my initial velocity is going to be 8 meters per second. It's going to be positive again, right? What will be the magnitude of the car's velocity after 10 seconds? So they want to know the magnitude of the car's velocity after a certain amount of time. So that's going to be the final velocity. So what do we not have here? No delta x. So we've got to pick the no delta x equation, which is the acceleration equation. So we go with A equals VF minus VI over T. So we've got to solve this. I'm going to take a moment to talk a little bit about algebra. You guys know order of operations, right? Who remembers the old PEMDAS? Oh yeah, right? So first we do parentheses, then exponents, then multiplication, division, then addition and subtraction, right? So what's kind of weird with doing algebra is we're actually going to kind of follow our order of operations when we go to solve for something, right? So we want to get VF by itself. So we've got to look at VF and be like, okay, what's connected to the VF, right? We have this t here, right? So I'm going to multiply by t on both sides of the equation, right? A little multiplication division. Let's do that first, right? So now we have AT, that's where it's at, equals VF minus VI, right? Okay, now I've got addition and subtraction. So I'm going to add that VI to the other side. And we end up canceling out that VI, and we end up with the final equation of VF equals VI plus AT. Hey, did we do this algebra already? We did. This is going to be a common one. Maybe it's worth remembering that this is a common rearrangement of that equation and something we might want to keep in our back pocket, aka your reference tables, to solve these problems later. So now that we've got that, now we can go and plug in our values, right? So VF is going to be equal to 8 meters per second plus 6 meters per second squared times 10 seconds. Amazing. So we have 8 plus 60, which is going to be 68 meters per second. Awesome. All of our numbers were positive. Everything was great. What I want to do now is, I'm noticing this wasn't here, so let's just write a new problem real quick. Here, what is the final velocity of an object that starts here, let's say starts from rest and is dropped off of a 20-meter high cliff. Okay, so we're going to follow the same process for this problem here. We'll start with delta x, vi, vf, a, and t. That's our chart. However, I'm going to do something kind of unique. We're dropping an object off of a cliff. So what is this object going to do? It's going to fall down, right? And it's going to accelerate downward as it goes. Is this object ever going to be moving upwards? Well, not in this case of this problem. Maybe if it's a bouncy ball and it hits the ground, it's going to bounce upward back, right? But we're not concerned about that. We want to know the final velocity of the object, so the object right before it hits the ground, or the speed of the object right before it hits the ground. So what I'm going to do is I'm going to say down is positive and up is negative. That's kind of weird. That's kind of backwards of what we often do. However, this object is only ever going down, so it makes sense just to keep and deal with all positive numbers the whole time. So let's start with this object. It's a 20-meter high cliff. So what is going to be the change in position or the displacement of this object? It's going to be 20 meters, and it's going to be 20 meters down. So we could put a positive 20 meters. The object starts from rest, so its initial velocity is going to be 0 meters per second. Its final velocity is what we're looking for. We want to know the final velocity of this object. And that's all the info that the problem gives us, right? But it gives us some more information in this word, dropped. When an object is dropped, we can go back to what we were just talking about in our notes. So, if you recall here, when an object is falling, all objects, regardless of their mass, fall at the same rate, and that rate is 10 meters per second squared. Right? 9.81 if we want to be picky, but we'll use 10 for the sake of this problem, just to keep the numbers easy. So this object's going to accelerate at 10 meters per second squared downward, because gravity's always pulling us downward, right? So everything's down. All of our numbers are going down, which is amazing. So let's look at the thing we don't have and the thing we don't care about. No time. So if we come back and look at our list of equations here, which equation has no time? That's right, the Boston equation. So let's use the Boston equation to solve this problem. We'll go with VF squared equals VI squared plus 2A delta X. All right, so do we have to do any algebra this time before we plug in numbers? The answer is yes, guys. We do have to do some algebra because of that. This equation is not solved yet for VF, okay? So we want an equation that's VF equals, not VF squared. So before we go about doing our algebra now, we first want to check, do we have any zeros? Is there anything that we can kind of cancel out as we go? The answer is yes, our initial velocity is 0. So this term, VI squared, is going to be 0. So we can rewrite our equation as VF equals 2A delta X. Or I'm sorry, VF squared equals 2A delta X. But we still have this squared here. So how do we get rid of it? Well, just like doing order of operations, right? We've got to undo that square. We're going to do the square root of both sides of this equation. The square root of VF squared is going to give us VF, and we are left with the square root of 2 times A times delta X. So now, once we have that, now it is time to go plug in our value. So VF equals the square root of 2 times 10 meters per second squared times 20 meters. And let's hit our calculator up for this. And I like doing this kind of all in one step, guys. I think it's very important to do this all in one step. So we'll go square root, we'll open up our square root first, and then we'll go 2 times 10 times 20, right? So everything under the square root, we hit enter, and we get our final answer of 20 meters per second. And that is down, right? We got a positive answer, and as we talked about earlier, positive is down. So there's our final velocity. So I'm hoping going through this process and doing a bunch of examples was helpful to you guys. There's a bunch of things on Google Classroom that are posted as assignments. I'd like you to have them all done by Friday. And then, ladies and gentlemen, that'll pretty much do it. I'm gonna be back soon, gonna be back right after Thanksgiving. So we'll get all of these done by Friday, get you guys kind of comfortable with working this, and then a few challenge problems on the Thanksgiving week, and then we'll call it a paternity leave, and I'll be back and we'll do some labs and some fun stuff. So hope you guys enjoyed this video, and I'll catch you later. See ya.